Welcome to my kitchen. What do I have here? So here I have a paper clip that I've basically just straightened out into, just a straight piece of steel wire. And I have a pair of tongs that I'm going to hold it. What am I going to do? I'm going to heat up this paper clip. Just give me a second to get it started. So here I'm holding the paper clip, and what am I going to do? I'm basically going to heat up part of the paper clip until it's super hot, until it's like as hot as I can get it with the flame from my gas stove. So you can see it's glowing orange. Can probably even get it to glow yellow. Yeah, that's looking pretty hot. Looking pretty hot right there. Alright, and now what I'm going to do is I'm going to let this cool down pretty slowly. So I'm basically going to let that side that I heated up cool down really slowly. And you can see, there's a little bit of oxidation on the surface right here. So what are we going to do? Well, we're actually going to explore today how heating and cooling down metals can alter their microstructure, and by altering their microstructure can end up altering their mechanical properties. So we're going to make a comparison between the side that I heated up, the sort of hot, kind of burnt looking corroded side, and then the other side right here that that I was holding on to that basically remained at nearly room temperature the whole time. So we'll make that comparison later on in today's lecture. Welcome to Biomaterials. What are we going to talk about today? We're going to talk about today the connection between the microstructure of metals and the yield strength of metals. And by sort of understanding some of what goes on for the microstructure of metals, and particularly how they deform and how they deform close to yield, we'll be able to sort of understand why some metals are stronger than others, or metals that have been given treatments in some way can be stronger than others, and how we can, as engineers, actually use temperature and other effects to control the desired strength of metals. So how are we going to break this lecture down? First, we're going to talk about the what the microstructure of metals actually is by looking at grains, and we're going to then zoom in even a little bit more and talk about the crystal lattice. I'm going to sort of zoom all the way down to the atomic level. And we're also going to talk about how metals, this crystal lattice and the grain structure of metals is not perfect, but rather that there are imperfections. There are imperfections in this crystal structure, and it's actually these imperfections that really govern some of the permanent deformation that leads to some metals having a high yield strength and some having a low yield strength. So, and these imperfections are given a special name in the context of metallurgy. They're called dislocations. So these dislocations are the special name that we give to imperfections in the crystal lattice of metals. If you remember from an earlier lecture, I said that some materials, particularly ductile metals, fail when the shear stress within that metal exceeds some threshold amount. So we're basically going to look at what happens to this crystal lattice when we apply shear stress. So, essentially what's happening to individual atoms when we apply shear stress to the crystal lattice, and how does that shear stress result in deformation, and in particularly permanent deformation, if we're sort of interested in how it plays into the yield strength right here. And it turns out that this permanent deformation that arises from excessive shear stress is related to dislocation motion. So essentially these imperfections within the crystal lattice actually sort of move through the crystal lattice. And again, we'll use lots of diagrams and visuals to help explain this. But these dislocations basically move through the crystal lattice, and that dislocation motion is basically what gives rise to permanent deformation. So dislocation motion, which essentially results in permanent deformation, which we would describe macroscopically as taking something past its yield strength. Since this dislocation motion through the crystal lattice basically ends up having a connection to the grain structure, it sort of has connections to the grain structure of the material. We're then going to take a closer look between how the boundaries between grains of the microstructure, so again, these are not the grains you eat, but rather grains that make up the microstructure of metals. We're going to look at the connection between grain size, or grain boundaries, and dislocation motion. And this connection between grain boundaries and dislocation motion ends up having an effect on the yield strength, or the connection between yield strength and grain size. Basically, the size of grains determines how frequently these boundaries happen, which has a connection to dislocation motion. So in a sense, the yield stress basically has a strong connection to what's happening at the microstructure. And it turns out that we can actually sort of quantify this effect between the yield stress and the grain size for particular metals, for most metals, through this relationship called Hall-Petch. So the Hall-Petch relationship, basically, it's an equation. I'll put it down once we get to that point in the lecture. But Hall-Petch is basically a quantified relationship between yield strength and grain size. And then you can say, hey, Lannon, if grain size is so important to yield stress, and you can imagine yield stress is so critical to a lot of the materials that we choose for various applications, what control do we have as engineers over grain size? And it turns out the control we have over grain size is what I sort of started to show in the Welcome to My Kitchen segment. But the mechanism by which we can control grain size is through heat treatment. And basically this heat treatment can basically change grain size. And it turns out we sort of have like two different names for sort of two main heat treatment processes that kind of do opposite things. One is called quenching, and another, and its sort of opposite, is called annealing. And basically, by controlling temperature, and in particular how temperature varies with time, we can quench or anneal metals to change their grain size and ultimately change their yield strength. So that's where we're headed in this lecture. Let's now get started with this discussion of what's happening, what this microstructure of metals look like in terms of grains, and zoomed in even more in terms of crystal lattice. So if we were to zoom in, sort of zoom in on a metal, and you can actually see this with certain microscopes, and the visualization can be enhanced if you sort of polish and etch the metals with in a particular way, but you can see it even without it. If you zoom in, you can basically see that metals are actually made of multiple crystals. And these, this crystal might sort of these crystals might look like this. And just to sort of give you a sense of scale, I mean, it varies. Obviously, it varies depending on heat treatment and all this stuff. But a typical size, for one of these crystals might be on the order of tens of microns. So tens of micrometers, right there. And these crystals sort of have kind of a texture to them almost, and you can actually see it if you etch these metals in particular ways. But basically there's this crystal structure, and you can almost see there's sort of a texture to each of the crystals. And this sort of microscopically but not atomically visible texture is has connections kind of all the way down to the atomic scale. So, we can sort of see some kind of texture or orientation to these crystals right here. But if through the if you had sort of an even more kind of magical microscope, if we zoom in more, you could basically see the atomic crystal lattice. So these multiple crystals. One crystal is what we call, another name for these sort of crystals is we call them grains. And if you somehow could magically zoom way in on all the grains, and somehow had some way to actually see individual atoms, you would see that the atoms within these grains line up into sort of a regular crystal lattice. And the exact way the atoms arrange themselves in a crystal lattice depends on what the chemistry of that metal is. But you can kind of imagine, for sort of simplicity's sake, that they might arrange themselves in sort of a grid like this. Where each one of these is an atom of the metal that we're looking at. And in an earlier lecture we talked about how ceramics arrange themselves in a grid, but metals do too, of course, not sort of alternating plus minus, but just sort of all being the same as one another, and sharing their outer electrons in a sort of metallic bond between all of them. So they arrange themselves in this regular structure, and they sort of form these metallic bonds between them. So we can almost imagine sort of a grid of bonds. A grid of bonds occurring between these atoms. But sometimes, no grid structure is perfect, and sometimes when these crystals were forming, there were imperfections, even sort of within these crystals right here. So we might sort of have one kind of grid like this, but then there might end up being some kind of shifted grid, some sort of shifted grid underneath them. And I'll sort of draw this on another piece of paper because, spoiler alert, I'm going to be moving it around a little bit. But we can sort of see, what might happen if there were like another grid underneath this one. So, all of these atoms are all bonding happily to each other in a grid. And you might imagine if, if this grid is next to this grid, how are these going to line up? Well, there's an unfortunate game of musical chairs. Musical chairs is this game where people play where there's sort of one extra person compared to however many chairs there are, and you try to sit down as quickly as possible, and someone is left standing. Well, that sort of happens with these atoms as well, that these guys bond to these ones, these ones bond to these ones bond to these ones, and then this one right here is kind of left without a partner. So so what happens? Well, this one's left without a partner, and it's, for right now, that just kind of remains how it is. So and these sort of atoms that are kind of left out are what we call dislocations. So the atoms that are left out, or the spaces between them, or this phenomenon in general, is what we call dislocations. This is one example of a dislocation. There are other types of dislocations, but for simplicity's sake, let's just focus on this one today. So, grains are basically what we see on the scale of microns. If you were to zoom way in, you would see the crystal lattice, which is what we see as an arrangement of atoms. And these crystal lattices have imperfections where basically you can imagine there's sort of one extra row or one extra column of atoms. And if this were to sort of, here I'm drawing sort of like what a 2D slice would look like, but of course these things are actually in 3D. So in a sense, this is actually sort of an extra plane of atoms kind of flipped in right here. So this is what we might call a dislocation. So now let's talk about what happens to this structure here when we start applying shear stress. How does it deform? And spoiler alert, what happens to these dislocations when we apply shear stress? So just imagine I start applying some shear stress to this material, and if you imagine, shear stress kind of wants to push one part of the atoms one way, and you can imagine that shear stress might push this part of the atoms this way, right? This is the essence of what shear stress is. And you can imagine if I started shearing this structure a little bit, originally, let's say before I started the shearing, this atom right here was closest to and wanted, I'll anthropomorphize it, but wanted to form a bond with this atom. But after shearing, if I shear it just a little bit, well, if I shear it just a little bit, it still remains close. It still remains closest to its atom. So with small amounts of shear, all our neighbors stay the same. So all of our neighbors stay the same. But with large amounts of shear, the dislocation jumps in the formation of new neighbors. So what does that mean? So if I shear this structure enough, now instead of wanting to be neighbors with this guy, this one wants to be a neighbor with this one. And then what does that mean? Well, if these still stay neighbors with each other and these are now neighbors, then the dislocation essentially becomes a new atom, sort of becomes the new dislocation. So in a sense, this dislocation sort of shifted with a small perturbation of the atomic structure. This one instead of being friends with this one is now, if I shear it enough, now becomes friends with this one. But some of the other structures can still remain primarily bonded to their original neighbors. So what does that mean? That means that basically the dislocation moved. Physically atoms didn't really, it's not like the atoms themselves actually jumped, but sort of the atom identified as the one that not having a bond is now a different one. And then when I let go, this atomic structure down here doesn't go all the way back to where it was before, but it settles only part way back to where it was before. So with large amounts of shear, dislocation jumps to new neighbors, and basically the structure below doesn't go all the way back. And what does it mean if the structure below doesn't go all the way back? This, in a sense, is what we would basically describe as permanent deformation. And if we were to sort of look at, what happens with small amounts of shear versus what happens at large amount of shear, we can do so in the context of stress-strain curves, like we talked about before. So, here's our stress-strain curve for a ductile metal. If we're doing this with just small amounts of shear, we're still staying on this elastic region. So basically, if we're staying in this elastic region, we're shifting this a little bit. We're shifting this a little bit, but not enough for any of these bonds to hop over. Particularly the ones around these dislocations, not enough for those bonds to hop over to a new neighbor. Right? So when we let go, everything settles back to where it was originally. But with large amounts of shear, macroscopically, this means we kind of went up like this, went over a bit, and then went down, and we're left over with this permanent deformation right here. And this permanent deformation on a very small scale might just be a couple of jumps of these, but if you imagine over the course of, if this phenomenon is happening all over the place within all of these crystals, then once you've done that, the accumulation of bajillions of these dislocations all scooting at the same time through these crystal lattices, ends up accumulating. So the accumulation of many dislocation jumps is basically equal to plastic deformation. And this is something we can observe macroscopically when we do stress strain. When we look at stress strain curves. So this is how dislocation can lead to permanent deformation. Basically, they play a game of musical chairs, and who comes out losing? Well, the atom that was originally part of a dislocation becomes, now gets a partner, but leaves its neighbor open-ended. But then, you can imagine this process kind of continuing over and over and over and over and over again, where the dislocation motion hops not just once, but again and again and again and again and again, if this strain, if the stress is sustained, sustained for enough time. So that's basically how dislocation motion can lead to permanent deformation. Now let's talk about what happens once we get close to grain boundaries and how that influences dislocation motion. So earlier in the lecture, I basically talked about these grains, and what I'm talking about here is something occurring entirely within one grain. But what happens once we get to the edges of grains? Well, let's take a look. So what happens to dislocation motion when it reaches a grain boundary? And what even is a grain boundary anyway, right? What does it look like if we zoomed in on the grain boundaries, right? If we, what would it like? Here I sort of draw what it would look like if we zoomed in all the way in the middle of a grain, but what does it look like if we sort of zoomed into one of these interfaces right here? So let's zoom into a grain boundary and see what it looks like. Well, if we look at a grain boundary, we can kind of imagine it's sort of the interface between sort of multiple crystal orientations, right? So each grain has an orientation. Has a lattice orientation. And they're all different from each other. Basically, one crystal started forming, another crystal started forming, another crystal started forming, and they weren't touching initially, and they basically grew and grew and grew until they reached one another. But, I don't know if you've ever looked at like a road, like a map of the roads of a city of Boston, but it's kind of like the streets in the city of Boston. There's like a grid in one way and Back Bay, but then when you get to downtown Boston, there's a different set of grids and a different set of grids, and it's a hot mess traffic-wise where they all meet up. It's sort of the same thing with grain boundaries. Like there's, let's say, one crystal structure right here. And then there's maybe a different crystal structure right here. And there might be yet a different crystal structure right here. And to sort of emphasize the orientations of these, we imagine that each of these crystals sort of has their own bonds within the atoms that make up those crystals. But at the interfaces, the bonding between those crystals is somewhat disrupted, right? So within a crystal, we have these very regular metallic bonds. But that's disrupted at the interfaces. So this is essentially what what grain boundaries look like. Is grain boundaries are basically all of these places where you sort of have one nice orientation of your crystal, another nice orientation of your crystal, but the angles don't match up. And so now let's imagine, what happens to dislocation motion when it reaches a grain boundary. Well, just imagine that a dislocation started somewhere deep in this crystal and was kind of traveling along, or sort of moving its way up, sort of between these two rows right here. So, it might move, it might jump and jump and jump and jump. I know I didn't actually draw a dislocation, but just imagine a dislocation started all the way back here. this dislocation would sort of move, it would sort of move its way through this crystal structure. Well, what happens when that dislocation reaches a grain boundary? So what happens? I guess you could pause and ponder for a second. I guess I could turn this whole slide into, or this whole page into a pause and ponder question. But what happens? Well, it essentially just becomes part of, it basically just becomes part of the grain boundary. So the dislocation basically just becomes part of the boundary. So what does that mean? That basically means it sort of, in a sense, it ceases to exist, right? It ceases to exist. To exist, right? Because now, it's basically part, it's, what was sort of an internal gap or internal mismatch, now is basically part of this grain boundary that was mismatched no matter what. And it basically can't, it ceases to exist, and it can't cross into a new grain. So in a sense, these grain boundaries halt dislocation motion. Right? So the key takeaway here is grain boundaries, which I'll abbreviate as GB. So GB, grain boundaries. Grain boundaries halt dislocation motion. So that's, and that has implications for sort of how easy it is to permanently deform materials. So if they basically halt dislocation motion, that basically makes it more difficult to impose plastic deformation. It makes it more difficult to impose plastic deformation on the material. So that's the connection between grain boundaries and dislocation motion, in the sense that grain boundaries halt. Grain boundaries halt dislocation motion. Now let's sort of think about how grain boundaries, dislocation motion might play into the yield strength of a material. So take a moment now, pause and ponder. Which material is stronger? One that has large grains or one that has small grains? Stronger, i.e. a higher sigma yield. Small grains or large grains? So take a moment now, pause and ponder. Consider which ones. Well, it turns out that the answer is the stronger material is one with small grains. So small grains is the answer here. Now, why might that be the case? Well, basically, if there are smaller grains, there's basically more frequent grain boundaries. And if there are more frequent grain boundaries, that basically means that each dislocation permits less deformation before it's terminated. Right, so if basically if it's the grain boundaries that halt this dislocation motion, then the more grain boundaries there are, the less distance each dislocation has before it just gets gobbled up. So by having small grains, basically there are much more frequent boundaries. There's much less distance that it can travel before it gets gobbled up. So the key thing here is smaller grains equals stronger. Equals a stronger material, something with a higher yield strength. And the way, and it turns out that there's actually a quantitative way to predict this relationship, right? If you've gathered enough data, between, that correlate grain size to yield stress or yield strength, then you can formulate that correlation in, mathematically. And that mathematical relationship is called Hall-Petch, presumably named after the people who helped study it. The Hall-Petch relationship. And what does it do? It basically predicts the yield strength as a function of a couple of parameters. There's one parameter called T sub I, and it's plus another parameter called K. So it's T sub I, which is one parameter, plus K, which is another parameter, times D to the minus M, which is yet a third parameter. So Ti, K, and D are all parameters. Ti, K, and M are all parameters, and D is the sort of average grain size in a material. So D is the average grain diameter. So D is the average grain diameter, right? And this would sort of have units of length. M is basically a material property, and it basically it's almost always 0.5 for most metals. So M is a material property. And M equals 0.5 for most metals. Take a moment now and think, what is the significance of T sub I? So take a moment now, pause and ponder. What's the significance of T sub I? And to get you thinking about it, what is sigma yield for very large grains? Well, for very large grains, D goes to infinity, and if D goes to infinity, you essentially have, a large number to a negative number. So that's essentially like 1 over a large number, right? A minus exponent, right? You could sort of think of this instead as T sub I plus K over D to the M, right? That would be another way to sort of write this expression right here. So as D gets big, this second term in the relationship essentially disappears, leaving only T sub I. So basically T sub I, it's a material property, and it's basically what sigma yield is when grain size is large. So this is basically what sigma yield is when grain size is large. So, and we basically said that, you know, as grains get smaller, yield strength goes up, and that's basically consistent here, right? If d becomes a smaller and smaller and smaller number, then k divided by a small number becomes large. And if k divided by a small number becomes large, then sigma yield increases as well, right? So basically, so what is T sub I? You could imagine this is essentially the worst possible yield strength for a material. It's basically the minimum. This T sub I is essentially the minimum possible sigma yield. It's sort of like a worst case scenario. T sub I is kind of a worst case scenario for sigma yield. You know, if we did a very poor job at getting small grains or something like that. And K is just another material property that sort of governs, you know, overall how important is the grain size to the yield strength, right? If there's a large K, then this term ends up sort of having a big effect. If there's a small K, then sigma yield is kind of mostly governed by this constant value rather than the second term here. So K is another material property that basically governs how important the second term is in the yield strength. So M, basically 0.5, T sub I and K are material properties, and the key thing here is these material properties, these are independent of grain size. But they do depend on the chemistry of the materials here. So if you have steel instead of bronze or instead of aluminum, steel and aluminum and bronze all have different T sub I's and different K's. But if you sort of choose one recipe of steel, then that T sub I and K for that particular type of steel is locked in, and you can but within that particular type of steel, you can still change the yield strength by changing the grain diameter. So it's basically independent of grain size, but depends on material chemistry. So, you might have heard of this alloy. So, alloys, by basically mixing steel with carbon or steel with other elements, is basically how they tweak T sub I and K. But heat treatment is basically how we can change the yield strength by changing D. So heat treatment basically is how we tweak D, and alloying iron with carbon or iron with other elements is how we change T sub I and K. So that kind of segues into the last part of this, which is basically how does heat, what's the relationship between heat and grain size, and in particular heat and time versus grain size, and what is this quenching and annealing, and how might that influence the mechanical properties of our alloys or of our materials. So how does heat treatment affect grain size? Well, it turns out that you've all seen, at least to some extent, or maybe even in the movies, people doing heat treatments to affect grain size. So you might have seen, in the movies, there's the scene where there's the blacksmith, and the blacksmith is pounding away
on a red hot sword, and then there's like a water bath, and the blacksmith plunges that sword into the water, and the steam goes up, and the sword cools off, and the blacksmith isn't just doing that. It wasn't just doing that plunge for dramatic effect. That rapid cooling by plunging in water is what's called quenching. So quenching is basically rapid cooling. Often via a plunge into water. Sometimes even oil can be used. So rapid cooling via a plunge into liquid. And this is basically what the blacksmith was doing to the sword. And what is this heat treatment process? Well, basically, if you heat up a metal, so if you heat up a metal, you change its phase. If you heat it up enough, and depending on exactly particular temperatures and something like that, you change phase. And the phase can actually be different solid phases before you reach a liquid phase. So many metals might have a solid phase. For example, at room temp. And then, if we heat it up, there's a different solid phase at some elevated temp. For example, at, let's say, orange hot. Obviously, there are precise temperatures for all of these, but you go from one solid phase to another solid phase at orange hot, and then if you heat it up even more, you might get a liquid. But it turns out that in order to sort of get this heat treatment process, you don't need to do it all the way to a liquid. You can sort of do it by transitioning one solid phase to another solid phase. So let's imagine we start here. At this sort of orange hot solid phase. Actually, maybe I'll circle it in orange just to sort of emphasize, our temperature here, right? And when you're transitioning from one phase to another, either by heating up or by having it hot and going back down, you do a total recrystallization of the grain structure. So phase changes. You change its phase, and when you change its phase, you recrystallize. You recrystallize all of the grains, and when you do so, you usually start, and the new crystals start. New crystals start at grain boundaries. So new crystals start at grain boundaries. So what might that look like? Well, imagine I have my orange hot phase, and I'm going to sort of draw that in orange, and then I have my room temperature phase, which I'll sort of draw in blue. So imagine I have my metal, it's orange hot. It has a grain structure that it obtained in its orange hot phase. And then if I cool, right, so cooling, could for example be via quenching. If I cool it down, I now need to transition from whatever crystal structure I had when I was in this phase. I need to sort of grow a new crystal structure. So cooling, I grow new crystals. And this is something that you can observe even when you're cooling ice in your freezer, right? This recrystallization can happen from a liquid to a solid phase, but it can also happen from one solid phase to a different solid phase. And when we're cooling, we grow new crystals, and those crystals start at the grain boundaries. So you can imagine, let's say I was the blacksmith, right? And I took that sword and I quenched it into the water. I'm rapidly cooling it. And basically what happens is I start basically creating a bunch of crystals that might sort of start at these grain boundaries. So all of these crystals, they nucleate, and then they grow, where basically you can imagine on the atomic level, you can imagine sort of some crystals growing. It's basically atoms hopping over from being sort of in one arrangement, where the individual atoms sort of at a growing boundary, then just kind of like make small shifts in order to realign themselves with the new growing crystal compared to whatever crystal was, originally part of the old phase. So basically these crystals grow and grow and grow, but, it's not just this crystal growing all by itself. All of these crystals are sort of growing. And sort of subsuming the phase around them. So what does that mean? Basically, this crystal grows out, this crystal grows out, all of these crystals are all sort of growing out. And eventually, this crystal grows, and this crystal grows, and this crystal grows. This one grows and grows. And basically where the two crystals meet now becomes a new grain boundary. So where growing crystals meet become a new grain boundary. So growing crystals meet, they become a new grain boundary, and you can imagine, basically eventually all of these crystals will fully consume the old solid phase, and eventually you might have a grain, a set of grain boundaries that end up dividing, what each of these crystals was able to sort of consume before it ran out of juice and before it ran out of material and collided with its neighbors. So we end up getting basically a new crystal structure formed by the growth of all of these sort of nucleated sites. And you could imagine, the ultimate grain structure that ends up forming sort of depend on the relative rates of nucleation versus growth, right? So how many new grains form and how big are they? Well, grain size so size depends on relative rates of nucleation versus growth. So you can so what's the key thing with here? If you have fast nucleation, then you get small crystals. Where you can basically imagine if you have fast nucleation, you have tons of new crystals forming all at the same time. They all sort of grow out, but then they collide into each other very quickly because there were a whole ton of them forming all at once. So fast nucleation basically means we have many crystals forming all at once, and each crystal only gets a little bit of material before the whole material is recrystallized. if you have slow nucleation, then you end up with large crystals. And it turns out that that basically this fast nucleation with small crystals, this happens during rapid cooling. i.e. quenching. So this happens during quenching, right? During the blacksmith, right? And that's understandable, right? The blacksmith wanted small crystals to basically have a sword that had a very high yield strength. This slow nucleation with large crystals is basically what happens when we have slow cooling. And this slow cooling is basically what we call the opposite of quenching, which is essentially, in a sense, which is what we might call annealing. So if we have rapid cooling, i.e. quenching, then we get small crystals. If we have slow cooling, i.e. annealing, then we get large crystals. All right, so take a moment now. I have my paper clip. This side is basically not heated, and not heated and cooled. And this side right here was basically heated and slowly cooled. Slowly air cooled. So this was not heated, and this side was heated and slowly air cooled. And I want you to pause and ponder. I'm going to take this paper clip and I'm going to bend it. Which side does the bend? Which side will the bend happen on? Which side will the bend occur on? The side that was not heated, that sort of the shiny, right, unburnt, or the burnt side where it's basically heated and slowly air cooled. So take a moment now, pause and ponder, and consider and make a guess as to which one might be the case. All right, so hopefully you've had a chance to pause and ponder. Let's go ahead and do it. So I bent it. Which side did the bend occur on? The bend occurred on the side that was heated and slowly air cooled. Why? Well, let's there's more at play than just what I did to the paperclip. We need to think about what happened to the paperclip even before I got it. So this side right here that was not heated or cooled, before I even got this paper clip, the steel that went into this wire was heavily strain hardened. And when that steel was heavily strain hardened, it basically increased its yield strength. So basically, what the way they made this steel wires, they basically started with a very large cylinder, and then they basically put it through a bunch of successive smaller and smaller rollers / stretchers that basically turned what was, essentially like a cylinder like this into smaller and smaller and smaller cylinders, eventually bringing it all the way down to this wire. So basically the left side was heavily strain hardened, which increased the yield strength of the steel on this side, but all of that strain hardening was undone when I heated and slowly air cooled this right hand side. This was basically I annealed it. So basically I heated it up red hot. I did away with all of the grains. I did away with the small grain structure that was imposed by this process and created a new grain structure with large grains. So I annealed, I got large grains. By basically, rather than having a ton of small crystals all nucleating at once, I only had a few, and those crystals could grow to be really big before it took over. And of course, if we go back to Hall-Petch, if we have a really big diameter crystal, then our yield strength kind of goes back down towards T sub I. So basically, what did I do? I basically gave the heat-treated side a really lousy yield strength. So I basically heavily strain hardened. So this side was heavily strain hardened. This, I undid all of that strain hardening by basically heating it up and lowering its yield strength by increasing its grain size. So if we look at this paperclip now, this paperclip, each side of this paperclip essentially has two separate stress strain curves. The stress strain curve for the part that was not heat treated or cooled would look like this. So this is basically the strain hardened. The strain hardened, and it has a high sigma yield, and it has small grains. But then this other side, right here, it has the same modulus of elasticity, but the heat treating and slowly this I would say is annealed, and it basically has a low yield strength, large grains. But one key feature that we're looking at here is the annealing process gives us large grains, but it actually restores the ductility. Right? So when you strain harden, remember from a previous lecture, when you strain harden a material, you typically decrease its ductility but increase its yield strength. You can restore a material back to a lower yield strength and more ductility by annealing it. So it gives us large grains, but it also restores ductility. So in some applications where it's not important to have a high yield stress, but rather it's important to have a lot of toughness, sometimes what people will intentionally do to their metals is they'll do this process on purpose. They'll heat it and slowly, maybe not air cool it, but they might actually cool it over the course of several days or even weeks in precisely temperature controlled ovens to basically restore ductility. So under some applications, for example, the blacksmith quenching the sword, you might want, you don't care about ductility and you want a high yield stress. Under other applications, we don't care about a high yield stress, but we want a lot of ductility. And whether you heat or cool your metals quickly or slowly gives you that choice. Now, one last thought is the grain structure can be region specific. The grain structure can be region specific. So for example, to go back to the blacksmith quenching the sword, right? If we look at we look at the sword. This is the silliest sword ever, but whatever. If we look at the sword, that the blacksmith is quenching. Well, the surface actually cools quickly. So the surface cools quickly. Cools quickly. and the core cools slowly. Right? It's it's the surface of that core that contacts the cold water or the cold oil. The surface basically cools very quickly when it contacts the water, but the core of that sword, it takes time for that heat to make its way all the way out of the sword. So basically what happens is the surface cools quickly and we get small grains, which basically means we have a high sigma yield. And the core cools slowly, and this gives large grains. And this gives ductility. And actually this, in a sense, this is the best of both worlds for swords. Why? Because if you have a high sigma yield, this means it can retain a sharp edge. Right? That edge isn't going to wear out if the material that makes up the very edge of that blade has a high yield strength. But you can imagine, if you're going into battle against someone else and your sword smashes into their sword, I'm sure I could take a poll of this class, and I'm sure no one in the class would want a very brittle sword that's going to fracture into a million pieces if it strikes an opponent's sword. So what does that mean? It means we don't want our sword to shatter into a million pieces if it drops on the ground or hits an opponent's sword or something like that. We want a lot of ductility. So basically what happens is we want a high yield strength to keep a sharp edge, but we want the core of the sword to be ductile so the whole sword doesn't snap in half, right? This is why we make swords out of steel rather than out of glass or something like that. And of course, swords are like violent things that are designed to kill and oppress people. From a bioengineering perspective, these principles for the design of swords basically carried over into the design of teeth for bone saws or bone saw blades. So for bone saw blades, right, you can imagine the bone saw blade is made with a bunch of teeth, and these teeth are very precisely heat treated in a way where the most of the blade is ductile, but this is very strong. And you basically want, for a bone saw blade, you want the teeth not to wear out halfway through cutting someone's bone, but you want, if the surgeon's jamming the blade in there, right? A lot of force is involved in the cutting of bone, right? Bone is pretty tough stuff, and so if the surgeon doesn't want the saw blade to all of a sudden just snap partway through a surgery, right? So we want the blade to be very ductile. We want the teeth to have a high yield strength. So bone saw blades are quenched and heat treated in very precise ways in order to have a region-specific grain structure. So, hopefully this lecture has been helpful in drawing connections between the microstructure of metal and various properties like the yield strength that we care about, and we can gain some physical intuitions from considering what's going on at the atomic level. Thanks for watching, and good luck with your study of biomaterials.